Okay, we're on to section 19.5. And what we're going to talk about here is what's called Gibbs free energy. And now it's starting to get a little complicated because Gibbs free energy is kind of a hard concept to understand. What we're going to do is we're going to talk about what it is first. Then we're going to incorporate enthalpy and entropy as well as temperature into the prediction of what the sign of our Gibbs free energy will be. All right, so let's start from the kind of the beginning of where we left off, which is enthalpy and entropy. Now, when I dissolve ammonium nitrate, remember we talked about how this was an endothermic process, which is unusual. The sign is positive because it is endothermic. Now, the sign for delta S for this process is also positive because the ions in the solid crystal have more freedom to move around when the solid dissolves in water. And I want to note here that it is somewhat rare to find systems that have a positive enthalpy and a positive entropy as well. And we'll see that in a minute. Okay, now when sodium chlorine react together to form sodium chloride solid, right? So this is the reaction of the formation of sodium chloride from its elements. The sign of delta H is negative. This is not something that you would be expected to know. Either of these are. We would tell you this because the process is exothermic. Okay, this is just a summary of how this works. The sign for delta H for this process is negative. This makes sense because the reaction is sodium plus chloride. I'm going to put a 2 here, goes to 2 sodium chloride. I'm going from 2 particles to 1. So it would make sense that I could predict even that the sign, the delta H for that would be negative because I have 3 particles actually going to 2, and that means they have less movement. Now, I can write this equation. Delta G is equal to delta H minus T delta S. And this introduces a new concept known as what's called the Gibbs free energy. Now, what the Gibbs free energy is really important because what we're going to do is we're going to actually look at the thermodynamic favorability of a reaction to occur by combining the concepts of enthalpy and entropy. Okay, so this is enthalpy and this is entropy. Both of these need to be favorable in order for the reaction, this value to indicate that the equation is thermodynamically favored. Now, the sign of delta G gives us valuable information about whether or not a process is spontaneous. It was interesting, I was doing some reading about students and the word spontaneous. A lot of students think that spontaneous means it happens really quick, it happens right away. That is not what we're talking about here. What we're really saying is, will the reaction go unassisted or not? Is it thermodynamically favored? Remember that actions that are thermodynamically favored can be incredibly slow and happen over decades even. And so just because a reaction is spontaneous does not mean it is fast. Now, let's just look at the signs. If delta G is negative, the reaction is spontaneous. If delta G is 0, the reaction is at equilibrium. And if delta G is greater than 0 or positive, the reaction is non-spontaneous. In the forward reaction, and work must be done in order to make it occur. The reverse reaction, however, would be spontaneous. In a spontaneous process carried out at constant temperature and pressure, the free energy always decreases, right? A spontaneous process carried out at constant temperature and pressure, the free energy always decreases. Remember, we're going on the number line, we're going in this direction. Okay. Now, what we're going to do also is look at how favorability can, since we have already looked at this, the favorability of a reaction can also be shown by Q with respect to K. I can determine through Q and K whether my process is, through K, product favored or reactant favored. And then when I calculate Q, I can determine, based on its value with respect to K, which direction it's going to go spontaneously, to the left or to the right, until equilibrium is achieved. So remember we said that if Q is less than K, I have too many reactants. Therefore, if this is reactants and this is products, if I have too many of these, I'm going to shift my reaction in this direction. It's going to shift to the right. If Q is greater than K, I have too many products. So my reaction is going to shift this way to make less of them until it has reached equilibrium. If Q is equal to K, the reaction has achieved equilibrium, right? Okay. Now, let's look at how the Gibbs free energy is related to both enthalpy and entropy. There's an equation in your equation chart which looks like this again. If I'm given delta H and delta S, I can calculate delta G. This is basically just plugging everything in. Now remember, we do have this problem here. This one is in kilojoules. This one is in kilojoules per Kelvin. So I'm going to multiply entropy by T, which is going to get rid of my Kelvin. I'm good with that. But it's the kilojoules and the joules that are the problem. So we're going to convert all of our entropy into kilojoules, because in tables of values, delta G and delta H are listed in kilojoules, if you remember, and delta S is in joules. So when I go to plug this in, I'm going to put this value in. It is a negative 196.9 kilojoules minus T, which is at 298, because that's where I'm getting these values from my table. That is standard conditions. So automatically I need to remember that if I've got that little zero there, then it's going to be in standard conditions, which is 298 times a negative what? Well, I need to convert this to kilojoules. So there are 1,000 joules in 1 kilojoule, which means this value is 0.1896 kilojoules. 0.1896 kilojoules per K. This is K, so my K's go away, and I get a negative 140 kilojoules. Now, this means, since this is negative, this reaction is thermodynamically favored because the sign is negative. That means if I put these species together at room temperature and just let them sit, I will make SO3 in time. Maybe not quickly, but it will form. So, what we need to do now, and what you have to be able to do when looking at these values, especially for a multiple choice question, is you have to look at delta H and delta S and say, well, which one made the biggest impact? So if I look at these, this is a negative reaction, a negative value, and exothermic reactions tend to be favorable because there's no work that needs to be done. I don't have to input energy. This is a pretty big number. So this is definitely driven by delta H. Now, The entropy, however, is negative. That means that this reaction cannot be driven. A negative S cannot drive a reaction. However, a negative delta H can drive a reaction. That's because I'm actually going against nature, and that is becoming less random instead of more. So in this case, the reaction is driven by delta H. Now, let's look at this next one. Okay. In this case, I've got ammonium nitrate, which is dissolving into its ions, and I've got one positive delta H and one positive entropy. If I plug all this in, I get plus 26 kilojoules minus 298. Remember, I'm going to take this value, divide it by 1,000, and I get a positive 0.1087. And that turns out to be a negative 6.4 kilojoules. So this is also thermodynamically favored because this is negative. However, in this case, the reaction is not driven by delta H because this is endothermic, which means that the reaction requires work in order for it to occur, or energy input. But I can make up for this by the fact that I have a lot of entropy here. So although I need an energy input, this value is large. That causes this to become negative. So this reaction is driven by delta S. So I can also calculate delta G if I need to, using the same formation of products minus the sum of the formation of reactants, to do the same problem here as that I do for enthalpy and for entropy. All right, so if I look these up in a table, I get a minus 300 here, 0, and minus 371 here. So delta G is equal to, we're going to do products minus reactants again. And remember, this equation is also in your formula chart. 2 times minus 370.4, actually 371, sorry, I'm using two different tables of values here. Minus 2 times a negative 300 plus 0 gives me 140 kilojoules. Note that when I did that, that is the same value as I got up here. So I can calculate delta G using this equation or this equation and get the same answer. So let's summarize. In fact, I think what I'm going to do is I'm going to stop the video here so I can spend some time discussing this, because this is super important and it's going to take us a little bit. So I'm going to stop here and I'll see you in a minute.